As a fluid moves, it's generally squeezed and stretched and rotated as well as being carried about. In this film, we don't want to discuss the way it's carried about. Instead, we'd like to talk about the local distortion it undergoes and limit ourselves to flows at constant density. Before we're through, we're going to be talking about rate of deformation. But first, we'll look at finite deformation. That is, the local distortion that takes place in a finite time period. Now, when you think of the motion of a rigid body, after setting aside the translation, you're left only with the rotation. In deformable media, in addition to the rotation, we're going to discover that there's another component, the stretch or strain associated with the local change in shape. Now, by local, we mean to look at a part of the flow that's small enough so that looking at a smaller part doesn't change the picture. Now, this is a sketch of a two-dimensional velocity profile. This has a length scale associated with it, the radius of curvature. We want to look at a small enough piece of this so that there is no length scale associated with it, so that the velocity profile looks like a straight line. Now, we said that we weren't interested in how the fluid was carried about. That means that we ought to pick a point in here and draw our velocities relative to that point. If we do that, the fluid on one side will seem to be moving ahead, while the fluid on the other side will seem to be moving back, and of course the reference point will seem to be standing still. Now, let's talk first about two-dimensional motion. Now, this is the apparatus that we're going to use to produce a simple flow that we can talk about in detail. It has a motor driving gears that drive 4 pulleys around which run 2 endless belts. These belts form the walls of our channel. One moves one way and one moves the other. They produce a rectilinear shear flow in a very viscous fluid, glycerin. We say rectilinear because the streamlines are straight lines, and we're using the high viscosity of the glycerin to establish quickly for us a good scale model for those very small fluid regions we were referring to. Let me mark the surface of this uniform shear flow to reveal some of its characteristics. One belt is running one way and one is running the other, so that a flow is produced that has zero mean velocity. Notice how the point in the middle doesn't move in the laboratory frame of reference. Now let me just remove this pattern. That was easy, wasn't it? Now, I have here a multiple exposure photograph of this motion we've just been watching with pictures taken at 5-second time intervals. Now, with this pair of dividers, I can measure the distance between successive pictures of the same point. And they're obviously equal. Also, I can lay a straight edge along the path of a particular point. We can see that the paths are straight lines. So, apparently this is a steady flow with straight parallel streamlines, so that the displacement of a point ought to be proportional to its velocity. Apparently, the velocity profile is a straight line. Now, this flow has an important feature. I can put on the flow a number of straight lines. And you can see that they remain straight, even though they're turned and stretched as the distortion progresses. This means that there isn't any scale to the flow. Since the flow has no scale, it doesn't matter how big or how small the pattern is, it'll behave in the same way. And this is just what we wanted at the outset, a model for these very small regions where the velocity profile looked like a straight line. Now, we're interested in the motion relative to our reference point of the surrounding points. Now, let's be systematic about it and put on a circle of points so that they're all equally distant from the reference point and all equally spaced. As you can see, this circle deforms into an egg-shaped figure. It's not hard to show that this figure is an ellipse. It's called the strain ellipse. After we drop a pattern, the longer we wait, the more it deforms. One question we could ask is, where did the ellipse start from? If we could find that out, we might be able to measure the rotation. Let's try to analyze the deformation at a given time. If we take a picture after 25 seconds, we can compare it with the original configuration. Now, obviously, there's been both rotation and stretching. Because we put the larger marks on the circle, we can use these to measure the amount of rotation. But they don't all indicate the same amount. For example, here's one that hasn't moved at all, whereas this one has rotated all the way over to there. These variations show that a single measure of the rotation as a whole is not easy to find. But the ellipse does have features that the circle didn't have. It has bulges, and we may be able to use these bulges to measure the rotation of the whole figure. Now, these bulges represent the points of extreme strain. For example, here's the point that has moved farthest from the reference point, while here is the point that has moved closest. You can see that these points are also on the axes of symmetry of the ellipse, which, of course, are at right angles to each other. I'll use a solid line for the major axis and a broken line for the minor axis. Now, they might prove to be a convenient set of reference axes, so it would be worthwhile for us to see where they were on the original figure. Now, we can do that by counting marks. For example, the major axis here is about 1 3/4 marks over from the 90-degree point. That's 1 3/4 marks over. While the minor axis is about 180-degree point, 1 3/4 over. Draw those in. Major solid and minor dashed. It's clear that these are at right angles. So we've found a set of axes that were at right angles initially, and after the deformation are again at right angles. That could be a great convenience. Let's see how the rotation of this set of axes compares with that of other lines joining other points with the reference point. I can pick up the final configuration and put it right on top of the initial one so that the axes line up. There. Now let's look at how much a point rotated. Let's say 4 spaces to one side of the major axis. 1, 2, 3, 4. Now that went to a place 1, 2, 3, 4. Like that. And since its final position is clockwise from its initial one, why, it rotated farther than the special set of axes. But the ellipse is symmetric. I can go over to the other side here, 1, 2, 3, 4 spaces. And the final position, 1, 2, 3, 4 spaces. And that one, since its final position is counterclockwise from its initial one, that one apparently didn't rotate as far as the special set of axes. Now those two look to me to be about the same. If they are the same, since they're in opposite directions, they'll cancel out. So our special set of axes rotated an amount that's the average of the amounts rotated by the lines through those 2 points. But all the points on the ellipse come in pairs this way. The ellipse is symmetric. So this will work for any pair of points. This means that our special set of axes rotated an amount that is the average of the amounts rotated by all the points on the periphery of the original circle. It appears that practically by accident we've found what seems an ideal way to represent the rotation of our figure as a whole by specifying the angle through which this special set of axes has rotated. These axes are called the principal axes. We're going to find that these principal axes form the basis for our whole understanding of deformation. If we put the rotation back in and restore the ellipse to its true final position, we can see that in our case, the axes have rotated from there around to there, so that this angle measures the amount of rotation that this region has undergone in our time interval. But we've had to use these marks on the periphery of the circle in order to find the initial location of these axes. If we hadn't used the marks, we would have had to use something else, because a perfectly smooth circle doesn't have any angular references on it. Maybe we can find some other figure to indicate the initial position of our principal axes that's somehow more appropriate to the motion. The question that we want answered is, where were the points that end up on the principal axes? Now, suppose for a minute that we could turn time backwards. We'd see our ellipse changing back into a circle with the same featureless perimeter as before. This would tell us nothing new. Well, what could we usefully do with this ability to turn time backwards? Suppose at the end of 25 seconds there's a circle on the flow. What would happen to the circle as time ran backward? It seems reasonable we'd find some new information when time got back to 0. In fact, we'd expect to see an ellipse, but with a backward orientation. This idea of turning time backward isn't entirely without its point. I think you can see a sort of symmetry here. Let me draw on the axes of this ellipse, a solid line for the major axis and a dashed line for the minor axis. It'd be interesting to put these two initial patterns on the flow at the same time. That is a double pattern. The backward ellipse with its axes and the circle. Now the backward ellipse is turning into a circle, and the circle, as before, into an ellipse. Notice that the axes of the strain ellipse are growing out of the axes of our backward ellipse. But you shouldn't have been surprised. Look, it's in this direction that the most squeeze took place, with the major axis becoming the minor axis. It's in this direction that the most stretch took place, with the minor axis becoming the major axis. This backward ellipse is called the reciprocal strain ellipse, and these axes are its principal axes. Since they mark the initial position of the axes of the strain ellipse, we can use them to measure the rotation in our flow. Thus, the minor axis of the reciprocal strain ellipse marks the initial position of the major axis of the strain ellipse. And similarly, on this side, the major axis becomes the minor axis. Either one of these angles serves to measure the amount of rotation in our flow. Now, we've already noted two characteristics of the principal axes. First, they serve as average representatives of the rotation of all the lines. And second, that they lie in the directions of the extreme strain. There are two more properties worth investigating. When we first watched the deformation, we said it was distorting and rotating. We've examined the rotation. Now we should look at the distortion, or stretching. This stretching without rotation is called pure strain. And to study it, we can make up a pattern based on the reciprocal strain ellipse and its major and minor axes. Now, actually, we don't need the ellipse itself. We can just put in some lines parallel to the orientation of the axes. Now let's put that on the flow and watch it distort for 25 seconds. As it distorts, you can see that the lines that were parallel are remaining parallel, and the spacing is changing. Note that the angle between the sets of lines is also changing. While the deformation progresses, these sets of lines are not at right angles to each other. However, after 25 seconds, the lines are at right angles again, and we can use them for independent coordinates. Now you can see that the displacement of a point in the direction of one axis isn't a function of position along the other axis. This is a third important property of the principal axes, and again, it may be easier to see with the rotation removed. You can see that the lines have moved parallel to themselves in or out. Also, note that if a point was originally on an axis, its motion was directly in or out along that axis. Now, we can also define the principal axes as those that undergo no shear deformation, for these are obviously mutually perpendicular both before and after the motion. Now, three sets of mutually perpendicular lines, our principal axes and two other crosses, were used to build up this pattern. As the pattern is deforming, it's obvious that all the crosses are sheared. But after 25 seconds, the principal axes are again at right angles, while the other pairs of lines, which also started out at right angles, are no longer mutually perpendicular. And this is the fourth major characteristic of the principal axes. They are the only pair of lines that are mutually perpendicular before and after the deformation. Now, we've been looking at the deformation after 25 seconds. There's nothing special about that time. We should look at it at a number of successive instants and see how it progresses. Now, this is a multiple exposure photograph taken of the motion at equally spaced times. Now, I can form the reciprocal strain ellipses corresponding to each of these instants in our flow by just flipping the picture over. And I have such a transparency here. You can see that as the strain ellipse has been rotating one way, the reciprocal strain ellipse has been rotating the other way. So the initial location of the principal axes is different at every instant. That is, to form the principal axes of the strain ellipse at successive instants, the fluid has to start from successively different locations. Put another way, this means that different fluid makes the axes at every instant. To describe the deformation as a function of time, we should give the amount of rotation, the amount of strain, and the orientation of the principal axes of the strain ellipse at every time and for every neighborhood in the fluid. As we've been describing it, this would be in terms of the present location of the points as a function of their initial position. This is called a Lagrangian specification. The Lagrangian specification is of great interest in a solid as a description of deformation. And it's also frequently of interest in a fluid. But in a fluid, there isn't any primeval undeformed state to serve as a reference. Every state is in about as good standing as every other. In a solid, the material is tied to its initial location. It can never get very far away from it. In a fluid, on the other hand, in an unsteady, inhomogeneous flow, the relation between the present state and the initial state can be terribly complicated. For that reason, in a fluid, we're very often interested in the rate of deformation at a particular place, at a particular time, using the present state as a reference. That is, the rate of change from the present state, the rate of change, and so on. This lets us sit at a particular place and watch things go by. Such a specification is called an Eulerian specification. And is often easier to work with. Now, how many derivatives you have to give depends on how complete a specification you need, and that depends on what you're going to do with it. The common reason for describing deformation is because stress depends on it. In many fluids, stress is a function only of the present rate of deformation. We're going to limit ourselves to a discussion of deformation rate. Now, since we're interested in the present rate of deformation, let's define the instant that we've been calling the initial instant as the present. That is, the instant of special interest to us. Now, let's talk first about the rate of rotation. We've determined that the amount of rotation at any instant can be measured by the angle between the principal axes of the strain ellipse and those of the reciprocal strain ellipse. We could use a picture like this to measure the rotation rate at the initial instant, where, of course, the solid lines represent successive positions of the major axis of the strain ellipse, while the dashed lines represent corresponding positions of the minor axis of the reciprocal strain ellipse. We can measure the angle between positions of the axes at instants successively closer to zero, extrapolating to obtain the rate at the initial instant. However, there's a more direct way for us to measure the rotation rate. But first, we need to be sure just where the principal axes are at the initial instant. If once more we were to turn time backward, we would see the principal axes of the strain ellipse and those of the reciprocal strain ellipse approaching each other as time went to zero. At the initial instant, we find our circle restored and our axes occupying initial positions 45 degrees symmetrically on either side of the vertical. Now we need to determine the angular velocity with which these axes move off. Now actually, we're interested in their angular velocity just as they occupy the 45 degree and 135 degree positions. But we can see this more clearly if we have a little advance warning. Let's start well before, say 25 seconds before, and direct our attention to the period on either side of the initial instant. Now, we already know how to mark the fluid with a pattern which will become a circle after 25 seconds. The lines that will occupy the 45 degree and 135 degree positions at the instant of interest are solid, while the others are dashed. Let's try that again and watch the solid lines. Notice that as the solid lines come up to and pass through the instant of interest, the dashed lines move toward or away from them symmetrically. At the instant of symmetry, the velocities of the solid lines represent the average angular velocity of the pattern. Twice this angular velocity is what we usually call the vorticity. Now, what we've just seen suggests that perhaps the principal axes have an angular velocity that's the average of those of the other lines. That wouldn't be a surprise, since we already know that the principal axes have an angular displacement that's the average of those of the other lines at every instant. Now let's try something a little different that will average the angular velocities of a more representative sample of points. These little floats that support this rigid body just above the surface are small enough and far enough apart not to seriously affect the flow. We can expect the circle to rotate at the average angular velocity at the floats, so that there will be as much clockwise drag as counterclockwise from the relative motion. We should be able to remove this rotation by rotating our frame of reference. Watch the crosshairs on the circle. As we match the rotation of the circle, the walls of the channel appear to revolve in the opposite direction. Now that we've decided on an angular velocity, let me remove this circle. I want to put on a pattern that consists just of the lines that will become the principal axes at the initial instant, and view it from this rotating framework. At first, the figure is stretched out in the 135-degree direction. It comes in along this direction. Reaches a circle, and expands again in the 45-degree direction. Let's use the 135-degree and 45-degree lines, the principal axes at the initial instant, as coordinate axes. All we have to do is to start our rotation at a different time relative to the time at which the fluid is marked. Now you see the bulge coming in slightly to the right of the new ordinate, but approaching the ordinate as the figure approaches a circle. As the figure passes out through the circle, the bulge moves out along the abscissa. At the instant that the figure passes through the circle, the velocity is inward along the ordinate and outward along the abscissa. Since in our rotating frame of reference, the velocity is precisely inward along one axis and outward along the other, we can easily see why the axes can be the only pair of lines that are not changing direction at the instant of interest. And thus we can see why we can use this pair of lines to measure the rate of rotation of our fluid region. In addition, at the instant of interest, you can see that these axes are in the direction of the maximum rate of stretching and shrinking. These axes are called the principal axes of strain rate. So, in this rotating reference frame, we've already seen three of the properties of the principal axes. At the instant of interest, they mark the direction of extreme strain rate. They represent the average angular velocity of the fluid, and they are the only pair of lines that are not changing angle relative to one another. Now, from our earlier experience, we might also expect to find a fourth property of these axes. We observed this before by putting lines parallel to the axes. As you can see, the lines remain parallel and move toward or away from the axes. This means that the velocity parallel to the ordinate is not a function of position on the abscissa, and vice versa. We've seen how similar is the analysis of deformation rate to that of deformation itself. They can both be analyzed into a rotation and a stretch. In both, there are principal axes that serve as average representatives of the turning, that lie in the directions of the extreme stretch and whose directions aren't changed by the stretch. There are differences, of course. The principal axes of strain were continually changing direction as the deformation progressed. The principal axes of initial strain rate, of course, only occupy one position. Generally speaking, deformation rate is easier than deformation, but that's because we can sit at a fixed point and use an Eulerian specification. But that shouldn't be any surprise that it's easier, because after all, it's only the first derivative of the deformation at the initial instant. It's lucky for us that for Newtonian fluids and for many non-Newtonian ones, deformation rate is all we need. Now, what changes do we have to make to extend our observations to more general three-dimensional situations? Well, not many. We have ellipsoids instead of ellipses. Our velocity profile is a plane instead of a line. We have three principal axes for flow to be in and out along. We can't get the reciprocal strain ellipsoid by simply turning over the strain ellipsoid, but it is defined the same way as the surface that turns into a sphere. Deformation can still be analyzed into rotation and strain. Deformation rate into angular velocity and strain rate. The principal axes still represent the average rotation. They still are in the directions of extreme stretch, and they are still the directions that aren't changed by the stretching. Strain rate in one coordinate direction is still not a function of position along the other two axes. So we can see that the observations that we made in the steady, two-dimensional, homogeneous flow can be extended to more general situations. And of course, the local deformation, which we modeled with our linear shear flow, is the basis on which we build our understanding of the more complex deformations which we normally encounter.